Suppose P is a prime congruent to 1 mod 4. Show that P minus 1 over 2 factorial times P minus 1 over 2 factorial is congruent to negative 1 mod P. So this was a question that I had on my number theory final, and I think is a very good number theory question. So something I just want to point out in the beginning is that P minus 1 over 2 is the halfway point if we count all the factors, if we count all the numbers from 1 to P, whatever P is, P minus 1 over 2 will be around halfway. So if P is 7, then P minus 1 over 2 is 7 minus 1 over 2, which is 3, and 3 is halfway between 1 and 7. So how to do it? We first start off by stating Wilson's theorem, which is that P minus 1 factorial is congruent to negative 1 mod P whenever P is a prime number. And what I'm going to do is I'm just going to start pulling out factors of this factorial. So we'll have P minus 1 times P minus 2 factorial, and then we'll have P minus 1 times P minus 2 times P minus 3 factorial. And we can basically do this until we get to the halfway point. So we'll end up at P minus 1 over 2 plus 1, which is right above the halfway point, and P minus 1 over 2 is right below the halfway point. And so now that we have this whole expression, I just want to verify that P minus 1 over 2 is in fact an integer. So we know it's assumed that P is congruent to 1 mod 4. That's an assumption. So that implies that P minus 1 is congruent to 0 mod 4. And this means that 4 divides P minus 1. So we have 4 divides P minus 1. And by the transitive property of divisibility, which is if A divides B and B divides C, then A divides C. So we can say that 2 divides P minus 1 because 2 divides 4 and 4 divides P minus 1. So since 2 divides P minus 1, then P minus 1 over 2 is in fact in Z. So I'll just restate. We have P minus 1 times P minus 2 and so on all the way to P minus 1 over 2 plus 1, and all that times P minus 1 over 2 factorial. And notice that we have P minus 1 over 2 factorial already, and you can maybe see where I'm going to go from here. So I'll rewrite plus 1 to plus 2 over 2, and with the power of the modulus I'll subtract P, and we'll still have the same thing. Also note that we can rewrite P minus 1 and P minus 2 as negative 1 and negative 2 because P minus 1 is congruent to negative 1 mod P, and P minus 2 is the same as negative 2, and so on. So now we'll have negative 1 times negative 2, so on, times P minus 1 plus 2 over 2, and I'll rewrite P as 2P over 2, and this will give us negative P plus 1 over 2. And I'll just rewrite that as negative P minus 1 over 2. And so now you can probably clearly see that this is the same as P minus 1 over 2 factorial. It's just that we have negatives in all the terms, and if there's an even amount of these, then all the negative ones will multiply out to 1. But if there's an odd amount of them, then we'll get an extra negative term, which we don't want. So I'll just restate that since 4 divides p minus 1, p minus 1 is equal to 4k, and that implies that p minus 1 over 2 is equal to 4k over 2, which implies p minus 1 over 2 is equal to 2k, which is a restatement of what I said earlier, but you can see more clearly that p minus 1 over 2 is an even number. So that means if we list all the numbers from 1 to p minus 1 over 2, we'll have an even amount of those numbers. So we're going to have an even amount of these negative ones. So negative 1 times negative 2 times all the way up to negative p minus 1 over 2 will equal positive p minus 1 over 2 factorial. And so then we have p minus 1 over 2 factorial times p minus 1 over 2 factorial is the same as negative 1 mod p. And just a side note, if we were to suppose instead that p is a prime congruent to 3 mod 4, then we'd have sort of the inverse. We'd have p minus 1 over 2 factorial times p minus 1 over 2 factorial would be congruent to 1 mod p, because at the end here, we would have p minus 1 over 2 having an odd amount of numbers between 1 and p minus 1 over 2. So that would actually multiply out to negative p minus 1 over 2 factorial. And we can multiply both sides of the congruence by negative 1.